Hello. Hello, everyone. Happy New Year and welcome back. I hope you're excited to do some vectors. Today we're going to talk about vectors. And I've got some simple and some not so simple problems for you today, prepared for you today. So let's get started. And okay, so I'm going to share my screen. Okay. You should be able to see my screen right now. If not, please let me know. Okay. So 2024, and we're talking about vectors. And I hope everyone has seen the assignment. I hope it's not surprise. There's no surprise that the maths assignment is vectors. Vectors are used very much in physics, like mechanics at least is all about vectors. You need a decent understanding of vectors to become a good physicist. So let's talk about vectors. Well, a vector has magnitude and direction, right? So I hope this is no surprise to anyone. A vector has magnitude and direction. I think I've mentioned that. Magnitude is the length of the vector. Magnitude is the length of vector, or at least it's proportional to the length of the vector. And direction is, well, is the direction, right? So if this vector is A, then the magnitude of the vector is modulus A. That's how we write modulus A. So straight line, vector, straight line. That indicates the length of the vector. The direction. There are different ways you can say the direction. So you can say, for example, if this is 32 degrees, direction 32 degrees north of east, or you can say bearing of, so if this is north, the bearing would be 58, bearing 058. That's another way of saying the direction, right? So, I mean, there's no single way you can give the direction. Yeah, we typically use bearings, but you don't have to. You can say it's to the right, it's to the left, it's up, whichever way you like. Okay, so vectors have a magnitude and direction. Vectors have magnitude, and direction. Is this clear to everyone? Like on a scale of 0 to 10? I hope everyone understands that. Please let me know if that's not the case, so I can vectors have magnitude and direction. The magnitude is simply the length of the vector, or it's proportional to the length, and the direction is the direction. Now, we need to be able to add vectors. And we first, have you not done any vectors? Okay, no. Adding vectors. There are two ways of adding vectors. First is a triangle rule. The triangle rule. So for example, you have vector A and vector B. Okay, this is vector A and this is vector B. To use the triangle rule, what you need to do is you take this vector, draw it like this, for example. You take a copy of this vector. You draw it from the tip of the first vector. And then you draw a vector from the beginning of the first vector to the end of the second vector, this vector. And this vector is vector A plus B. This is how you add vectors. Any questions? Any questions here? So you draw the vectors one after the other, and then you just add them. No? No problem? The parallelogram rule is slightly different, but technically it's the same thing. You draw both vectors from a single point. So you draw vectors one after the other. Draw vectors one after the other. Draw vectors from the same point. Draw vectors from the same point. So you draw the first vector, then you draw the second vector from the same point. That means like this. Then what you do is you complete a parallelogram. So you complete a parallelogram. And you draw a vector from the beginning. The diagonal is is A plus B. A plus B. And you can see that A plus B here and A plus B here are the same thing, right? They are the same vector. We've achieved the same result in two different methods. How well do you understand what I've done? On a scale of 0 to 10, please? There are 5 of you, so I should be receiving 5 numbers. Okay, thank you. All right, 1, 2, 3, 4. Vishaka, I haven't heard from you. Do you understand? On a scale of 0 to 10. Okay, good. All right. When you the first method is so both are used equally often. You can't really say when they're used, which one is used more. Let's look at an example. So here's a child on a swing. I'm going to use 2 different methods. So if you are a child on a swing, if there is a child on a swing, there are 2 forces acting on the child. The first force is the gravitational force, is the weight of the child, and it's downwards. That's the weight of the child, W. And the other force is the tension in the rope. And as you can see, the rope is pulling that way because the rope is under tension and the rope is pulling that way. That is the tension of the rope. Now, which method would you use here if you wanted to add the 2 vectors? If you want to add the W vector and the tension vector, which method would you use? Parallelogram or triangle? Very good. Parallelogram, because they are drawn from the same point, of course. Yeah, and we can do that. We can draw a parallelogram, and the resultant force which is T plus W, is the resultant force. And as you know, childs on a swing usually go that way. That's the way the child goes, right? So that because there are two forces and the total force is that way. Well, can you give me an example? What would the other force be? Like okay, you could let's say the child's mother is holding the child and pulling that way. So this let's call it M, the force of the mother. If you're holding your child, preventing them from flying, from swinging, then you have a total force of 0, because this force, the orange force, is the total of the two blue forces. Okay, so you kind of can forget about these two. Now there's only two forces, one forward and one backwards. So if their forces are equal, then the child is stationary. If if there's no force here, then the child will swing. There could be wind, but I mean, if the wind is so strong that it's affecting the way you swing on a swing, you shouldn't be swinging. Like today, the wind is horrendous. We had 60 mile per hour wind today. Everything was just flying around. Okay, is that clear? Any questions? You could do it the same way, but using the triangle rule. You could say, okay, I got this force. I got this force. I got this force. And you draw it from the end. The tension force, then W force, and then the total force is this one. It's the same force. So T plus W. T plus W. This is using the triangle rule. This is the parallelogram rule. This is the triangle. I should do them the other way around, but I hope that makes sense. Any questions? From the Parinaya, from this position, the child will go forward. The child will go forward from this position. Now, when the child is on the other end of the swing, and this is a tough thing to do. When the child is here, now you will see my best drawing of a child ever. Okay. I could have done it differently. Anyways, when the child is here, the forces are in different directions. Now you can see that you have the weight force. The weight force is that way. The tension force has now changed direction. The tension force is now that way because the rope is pulling that way. And if you draw the parallelogram, from this position, the child will swing back. Plus W. Now, the moment you the moment you reach the bottom, the force starts to slow you down. So it's a backwards force which is slowing you down, and then you stop at the top part, and then you pull back. And then at the middle, so until when you reach the middle, the force changes direction. It starts pulling you forward, and you start slowing down. You slow down, you stop, and then that force pushes you forward, and then the process repeats itself. This is well, I could do something similar here. So fed for motion. So let's put someone on the swing so we can push that way. And then you can push that way. So this sort of thing. This is how you swing. So you see, I'm pushing forward, I'm pushing backwards, and it's slowing down, and then it stops, and then starts going backwards. Then it's going backwards. Then I change the directions. First it slows down, and then speeds up in the opposite direction. So this is what the swing does. The swing pushes you one way, then pushes you the other way, etc. Okay. Right. Moving on. Adding multiple vectors. When you have multiple vectors to add, you are better off using the triangle rule, because you can draw the vectors one after the other. So let's say you have let's say you have these 4 vectors. I'm just gonna copy this because I'm a tad lazy. Okay, so adding multiple vectors. So let's say I want to add A, B, C, and D. So I take copies of the vectors. So A, B, C, and D. Okay, so what I want to do, take A, a vector A, then I draw a vector, and then take vector B, and I take vector C, and then I take vector D. And then this vector is the resultant of therefore this vector. So I'm just going to label them. This is A, B, C, D. And this vector is A plus B plus C plus D. Now, interestingly, no one has asked me, but do you have to does it work if you do it in a different order? So let's do it in a different order. So first I'm going to go C plus A plus D plus B. So, and as you can see, you still get the same result, even if you do it in a different order. C plus A plus D plus B. You still get the same vector, A plus B plus C plus D. Any questions here? Please let me know. If you can use column vectors here, you can say that vector A is 3, 2. So it's 3 across, 2 up. Vector B is 1, minus 3. C is 1, 0, because it's 1 and 0. And this is minus 2, minus 2. And you can actually do A plus B plus C plus D is equal to 3, 2 plus 1 minus 3 plus 1, 0 plus minus 2 minus 2. And all you need to just add them. So it's going to be 3 and then 2 minus 3 minus 2. So 3 minus 3. So it's 3 and minus 3. So it's this way. And it is. And as you can see, this vector is 3 minus 3, which is 3 minus 3. Okay. Work out the following and write your answers as column vectors. I won't do all of them. I'll just do A plus B perhaps. A plus B, and I'm gonna do this. So A plus B, I'm using the triangle rule here. A plus B, and this is going to be vector A plus B. So as I can see, vector A plus B, so A is 3, 2, and B is 1 minus 3, then A plus B must be 3, 2 plus 3, 2 plus 1 minus 3. That makes it 4 minus 1. 4 minus 1. And indeed, it's 4 and minus 1. You could get the same result if you use the parallelogram rule. So I'm just gonna, what's the best way? You could do it like this, or you could use the parallelogram rule. So you draw the vector B. You draw the vector B from the same point. Then you draw a parallelogram. And the diagonal of this parallelogram is the total. And as you can see, it's the same vector, 4 minus 1, A plus B. What's going on? Here it is. So here it is using the triangle rule, and the parallelogram rule. Okay. Please don't be shy asking questions, because I'd rather you ask me than if you don't understand something, I'd rather you ask me. So here they're asking us to add some vectors, and this is pretty straightforward. So you can use either rule. So let's okay. Would you like me to go through these questions? 1 for yes, 0 for no. So no, you wouldn't want me to go through these questions. So you understand them. That's good. That's good. With Parinaya, that's a 4. I'm not sure what that means. Number 4. 1, 2, 3, 4. This one. Is that? This one. Where you have two vectors in the opposite direction. Is that one? Second in the second column. Okay, of course. So this is, you can use the same rule. So you can use the triangle rule. So you draw the first vector, then you draw the second vector from here. And this is your total. This is your total. This is A, this is B, this is A plus B. Okay, does that make sense? Okay, good. You could also just, well, I mean, use common sense. If this is 8 and this is 3, the total is 5 up. Then, yeah. Okay, that's good. That's good. Resolving vectors into components. It's the opposite of adding vectors. If you have a vector, let's say vector C, this vector can be represented as a sum of two vectors. You could say vector C is actually equal to vector A plus vector B using the parallelogram rule. You can see if this is vector A and this is B. So C is equal to A plus B. All right. What would be an example? Well, let's say you have a sled. Not too much snow this year, but anyways, you have a sled and I don't know, there's something on the sled. Doesn't matter what it is. And somebody's pulling this sled. And so they attached a rope at this point, attach the rope, and they're pulling that way. There's a pulling, this is a tension force. Now, when you are looking at this problem, it would be easier if you had two separate forces. One like this, and one like this. So instead of one force at an angle, we can say it's equivalent to two forces. So we call this force Tx, the horizontal component. And we've called this force Ty as the vertical component. And this is T. So here, T can be represented as a sum of Tx plus Ty. And we call this horizontal component, and we call this the vertical component. So basically, instead of pulling this way, it would have the same effect if somebody was pushing up and somebody was pulling to the right. This is the idea of resolving vectors into components. And mathematically, it's quite simple. If this angle is theta, then you can use trigonometry and you can see that this is a right angle triangle, and sine theta is equal to Ty divided by T, because this is Ty, because it's the same thing as this, and this is T, and this is Tx, so cos theta is Tx over T. So from here, you can work out that Ty is equal to T sine theta, and Tx is T cos theta. As a general rule, if you have a vector f, for example, f, and it could be represented as a sum of two vectors. This is f, and the angle is theta. This is f cos theta, and this is f sine theta. This is a very useful result when you are working with vectors. Of course, we're saying about the magnitude of the vectors. When I don't write the arrow, I usually mean the magnitude of the vector. Does that make sense? On a scale of 0 to 10? Okay. Right. So resolving vectors into components. Now, this is not a single way you can do this, of course, because look, if you have vector c, so let's do vector c and write it here. We could say that vector c is the sum of this vector plus this vector, right? Because they make up a parallelogram. But it doesn't have to be this way. It could just as well be the sum of this vector and this vector. And these vectors don't even have to be perpendicular. You can have this vector and this vector. Let's call this E and F, G and H. So C is F plus E, and C is H plus G. And once again, here C is A plus B. So all three are valid, right? So it doesn't have to be horizontal and vertical. That's what I'm trying to say. The decomposition of vectors, so this is called a vector decomposition. We take a vector and we break it down into two vectors which are more convenient to work with. Because horizontal vectors are easy to add and vertical vectors are easy to add. But sometimes you don't need horizontal and vertical. Sometimes you need something else. So if you are on an inclined plane, so for example, I'll just Google a picture of an inclined plane. Inclined. Not very exciting. You have a mass on a slope. I'm just gonna stretch it like this slightly. You have a mass on a slope, and you want to draw the forces acting on the mass. And there are two. One force is down, is the weight of the box. This is the weight of the box pulling down. And then there's the normal reaction force. Normal reaction force is a force perpendicular to the surface. Normal reaction force, weight. And of course, well, you can say, okay, let there be friction. There's a friction force pulling that way. Friction force. Like, you can see that you could potentially break these two forces, this force and this one, into components. You can break down the friction into two components like this, and you can break the normal reaction into two components like this. However, it would actually be easier if you break down the weight into two components like this and like this. And we say that this is weight component of weight along, perpendicular to the slope, perpendicular to the slope. And this is the component of weight parallel to the slope. Component of weight parallel to the slope. Okay, getting more intense, right? Getting more and more interesting. We started simple and now we're going harder. So how well do you understand this? How well do you understand what I've just done? Okay. What I've done is I said instead of weight, I have the weight parallel to the slope and weight perpendicular to the slope. And yeah, you have something else. Which is into components. Why is this useful? Well, this is useful because if the box were to move, it would be moving along the slope. It wouldn't be moving perpendicular to the slope. Exactly, Vishaka. That's normal reaction force. Okay, that's a very good question. A normal reaction force is the force that arises when you attempt to push something. So if I have a book and my finger pushes the book, what's preventing my finger going through the book? Because I'm clearly pushing. You can see the book changing shape. The book is pushing back, and this force this is called the normal reaction force. Normal because it's perpendicular, reaction because it reacts to your action. Okay, the book is pushing back, and this is force. When you're standing on the floor, you have normal reaction force because your feet are pushing against the floor and the floor is pushing back. This is the normal reaction force. Does that make sense? Okay, good. Can you say that perpendicular force need to be equal? Yes. If the book was stationary, this force, we call this W parallel and W perpendicular. You would say that this one has to be equal to this force. W parallel has to equal to friction. And normal reaction has to equal to W perpendicular. W perpendicular is equal to the normal reaction force. Okay. So let's do an example, I'm guessing. Let's do an example. So you have a slope and you have a ball. A ball is sliding with no friction. So it's not rolling, because rolling is a whole other story. It's not rolling. So the angle theta is 30 degrees. And the ball has a mass, let's say 2 kilograms. Find the acceleration of the ball. Find the acceleration of the ball. Does anyone know how to solve this? You mean 20 Newton force downwards? Yeah, F equals ma. But what is F? Indeed, there's a downwards force on the ball, which is the 20 Newtons, because that's mg. M times g. Yes, g is 10. It's approximately 10, of course, Newtons per kilogram. Newtons. I'm just, you know what? I won't say 20. I just call it, in physics, we call it mg. Because you can always substitute. It's mg. The other force acting on the ball is the normal reaction force. And already we can see from the parallelogram rule that the ball will accelerate that way. Yeah, the resultant force on the ball is that way, so it will accelerate along the slope. Okay. Now we draw something that is called a free body diagram. Free body diagram. Free body diagram. So we draw the ball and the force is acting on that ball. Why 40? Sorry. You actually multiply by sign, not divide by sign. But we'll get to that. So you have two forces. You have the force. So by the way, this is the next topic. This is the next topic. You don't really need to worry about it. So we could, because it is accelerating along the slope, we are interested in what's going on along the slope. So we break down the weight into two components. we break down the weight into a component like this and a component like this. And if you are any good with geometry, you will notice that if you do this, that this angle is going to be 30 degrees. It comes from the similarity of triangles. I don't want to bore you with the details. It's because this is the next topic. The next assignment is going to be on this. Okay, there's going to be a lot of this in the next. So if you don't fully understand why it's 30 degrees, for example, so don't worry about it. So just believe me that this angle is 30 degrees. You can check. You can test it for your. You can check it for yourself. 30 degrees, and therefore, if we remember how to work with this, we can actually take a snapshot and just spin it around. It looks familiar, doesn't it? If this is theta and this is mg, what's this blue line? What's the length of this blue line? If this is mg, if the red one is mg and the angle is theta, using this rule, if this is f, mg cos theta, yes, this is mg cos theta, and this is going to be mg sine theta. So this is the normal reaction force. This is mg cos theta, and this is mg sine theta. And as you can see, mg cos theta has to be equal to n. So mg cos theta has to equal to the normal reaction force. So they cancel out because it's not moving up or down. It's moving along the slope. So ma is equal to mg sine theta. And then m cancels out. And acceleration is g sine theta. So g is 10 multiplied by sine theta. Okay. Acceleration is g sine theta. G is 10 multiplied by sine theta, sine 30 degrees. So 10 times 1/2 equals 5 meters per second squared. Okay. I know it's a lot to take in, but don't worry. I'm just demonstrating to you where this is used. So you can find the acceleration of a ball rolling down a slope by breaking down mg, the weight of the ball, into components along the slope and perpendicular to the slope. The component perpendicular to the slope, this one, cancels with the normal reaction force because the ball is not moving into the slope or out of the slope. It's just moving along the slope. And the only force along the slope is mg sine theta. And this allows you to find the acceleration. Okay, moving on. Problem 6. Find the magnitude and the direction of the resultant force. So what do we do here? We need to add all of these forces. Of course, we can use the triangle rule, and we can do it quite straightforward. So 3 newtons, 1, 2, 3, 3 squares, 2 squares plus 2, and plus 5, but at an angle. Now this bit is tricky. It's like this. So your result should be something like this. Okay. However, It's not very clear how to do this. So what we do is we break the 5 into components. We break the 5 into components and we say, okay, 5 can be replaced by 2 forces down and like this. So rather than doing that, I'm saying this, okay. This force can be broken down into 2 forces, down and like this. Okay. So this force can be represented as the sum of 2 forces. And this is going to be 5 sine 30 degrees. And this is going to be 5 cos 30 degrees. And we know that sine 30 is 1/2, so it's going to be 2.5. And cos 30 is square root of 3 over 2 is 5 square root 3 over 2. Okay, let's keep it 5 over 2. It's 5 over 2. Right, so this is just a sketch of what. So what we do here, we say, okay, this is the same as 3, 2, 2.5, and 5 square root 3 over 2. It's the same as 3, 5 over 2, 2, and 5 root 3 over 2, which is equivalent to, oh, can you do that? I was wrong. So 3 down the top minus 2.5, it's going to be 1.5 up, 0.5 up, sorry, 0.5. So it's 1/2 up. Yeah, because 3 minus 5.2 is 1/2. And then this could be written down as 5 over 2 root 3 minus 2. So doing this minus this to the left. So we have 2 forces. Yeah, so we can see the 2 forces. And this can be represented as one single force. So it's this force, the total of the 2. The total of the 2 is like this. Oh, because I messed it up. I messed up the length of the vectors because this is nowhere near to 5. So 5 would be like this. So at 30 degrees, this is roughly 30 degrees. So it should be here. Which is more like it. Okay. And so the length of the vector can be used. You can use Pythagoras to find the length. So magnitude is equal to the square root of 1/2 squared plus 5 over 2 root 3 minus 2 squared. I'm not going to bother trying to find the exact value. I'll just use my calculator. 0.5 squared plus 2.5 root 3 minus 2 squared. 2.38. So it's 2.38. So the magnitude. So let's say the vector is A. So the magnitude of A is 2.38. Magnitude is 2.38. And the direction, well, you can use trigonometry. So if you want this angle, theta, then this angle is, this is 0.5. So if you use a right angle triangle, this is 0.5 and this is 2.38. So theta is arc sine of 0.5 divided by 2.38. So 0.5 divided by 2.38, which is 12.1 degrees. Direction is 12.1 degrees north of west. Or you can say, if you fancy it, it's plus 270 or bearing 282.1 if you like it. So what I did is to add the three vectors, I first broke down this vector into two. Then I added the horizontal vectors and the vertical vectors separately. And then I used Pythagoras to find the magnitude, and I used trigonometry to find the direction. It's quite straightforward. Any questions? Do you think you understand how to do this? Because this is the same as question. You don't understand it, but you think it's interesting. Am I understanding it correctly? Oh, no questions. Because this is the problem 2 is exactly the same. Actually, problem 2 is simpler than that. Problem 2. Oh. Find the magnitude and the direction of the horizontal of the four forces. So you have 9 to the north, 9, 6 to the east, 2 to the south, and 2 to the west. And then you just find this using, you need to find the direction and the magnitude using Pythagoras, direction using trig. Okay. And what else? Subtracting vectors. We haven't covered that. Subtracting vectors. Oh, well, I think we did. I didn't mention subtracting vectors, but just in case, subtracting vectors. It's called problem 7. Problem 7, subtracting vectors. Vectors. If you have subtracting vectors is the same as adding. You know that if you do 7 minus 3 is the same as 7 plus minus 3. So the same thing with vectors. If you have vector A minus vector B is the same as vector A plus minus vector B. And if you have vector A and vector B, this is vector A and this is vector B, what you need to find is vector, if you want to find vector A minus B, so A minus B is the same as A plus minus B. So you need vector minus B. So you draw vector minus B, which is the same as B, but in the opposite direction. So this minus B, and you add those two vectors instead of adding the, instead of subtracting. So you do vector A, so you take vector A, and then you take vector minus B. So you can use the triangle rule here or the parallelogram rule. I'm going to use the parallelogram rule just because. And it's 3, so somewhere here. This is going to be vector A minus B. And interestingly, if you draw two vectors, vector A and vector B, and you complete a parallelogram, then this vector is going to be A plus B. So this is vector A, this is B. This vector is A plus B. But if you draw the other diagonal, let's say this one, this diagonal is going to be A minus B, A minus B. Okay. So let's say invent a problem. Invent a problem. Let's say you have a vector. Let's say a vector A is equal to 0, 5. And vector B is, it's going to be too easy. Okay, 2 and M. If equals modulus B, find M. Do you know how to do this? Do you think you know how to do this? Where's my chat? Well, we first need to work out what is A and B. What is modulus A? Okay, so just I'll just quickly go through this. Modulus A is equal to the square root of 0 squared plus 5 squared. And modulus B is equal to square root of 2 squared plus M squared. Because that's the length of the vector, the magnitude of the vector. You use is the square of the It's the square root of the sum of this square of the components. And then you just do, okay, this is 5, of course. So because they're equal, you'd say 5 equals square root of 2 squared plus m squared. In other words, it's 25 is equal to 4 plus m squared. M squared is 21. M is plus or minus square root of 21. So B is either B1 is 2 square root of 21, or B2 is 2 minus square root of 21. So 2 possibilities. Okay, so that's it. Now, I don't know if I should be talking about the scalar product. Why not? Let's introduce the scalar product of two vectors. Now, fundamentally, you need to understand that some yes, that is what we're trying to explore. Fundamentally, there are things that are vectors and things that are not vectors. Okay, like mass is not a vector because it doesn't have a direction. But and vectors are drawn vectors have components. Vectors have a horizontal and a vertical component, the x component, the y component, whatever you name it. In analytic, in linear algebra, the vector is defined as a pair, as an ordered pair of real numbers. Okay, so a number, so for example, 3.6 is a real number. But 3.6 and 2.1 is a vector. So they are fundamentally different. A vector is a pair of numbers. Or it could be a triplet of numbers, or it's a group of numbers, right? So it's a vector of this in 2D. It's a vector. When you add two vectors, you get a vector. When you subtract two vectors, you get a vector. However, when you multiply vectors, well, it depends. Depends on how you multiply them. So the scalar product of vectors. So if you take a vector A and you multiply by vector B, the result is modulus A times modulus B multiplied by the cosine of the angle between them. Cosine of the angle between the two vectors. And that, so this is a vector. This is a vector. But the whole thing is a scalar. So not a vector. It's quite interesting. It is the dot product. The scalar product is the dot product. Scalar product of vectors, dot product. As opposed to cross product, which is a vector product, which we will cover in year 13, I think. So vector product product, also known as cross product. I'll just give you a slight heads up. So if you have vector A times vector B, it's going to be modulus A times modulus B multiplied by sine of the angle between the two vectors multiplied by a normal vector. It's a right-hand side triplet. I won't be able to explain to you what this is because this makes the whole difference. This addition explains why this is a year 13 topic and not a year 10 topic. Well, dot product is not really a year 10 topic. I think it should be. It certainly is at COMPOS. Scalar product of vectors. So it's defined as this. If the vectors are for column vectors, A times B is going to be AX BX plus AY BY. So vector A is AX BX and vector B is BX BY. So you just very simple, very straightforward. So the two are equivalent. Just depends on how you do it. So let's test it. Let's do a simple example. You have a vector A and vector B. A, vector B. So A is 2, 0. So it's 2 squares and 0. B is 5 and 0. So modulus of A is 2. Modulus of B is 5. The cosine of the angle between them. Cosine of the angle between them. So the angle between them is 0 degrees. So it's cosine 0 degrees. And cosine 0 is 1. Very good. So A times B is modulus A, modulus B times cosine 0 degrees, which is 2 times 5 times 1, which is 10. So the product of these vectors is 10. So if the vectors are in the same direction, all you need is just multiply them, multiply their lengths. So that's easy. Let's test if it works with the columns. So 2, 0 multiplied by 5, 0 is equal to 2 times 5 plus 0 times 0, which is 10. So works. Same result. Okay, same result if you use this or this method. Okay, let's see if we can do two other vectors. I'm going to do a simple example. So you have vector C and vector so this is vector C, which is 0, 3. And this is vector D, which is 4, 0. Yes, usually it would. Zeno, yes, certainly. If you have them as columns, but you don't always have the vectors as columns, that's the problem. So here, so C is 3, of course, D is 4. So C times D is 3 times 4 times cosine, and the angle between them is 90 degrees, cosine 90 degrees, and cosine 90 degrees is 0. So it should be 0. So let's see if we get the same result if we multiply them as columns. 0, 3 multiplied by 4, 0. We get 0 times 4 plus 3 times 0, which is 0, of course. And yeah, so we've done an example where they are parallel. We've done an example where they are perpendicular, and of course anything in anything else also works. So depending on yeah. So this formula is a convenient way to find the angle between between the two vectors. So example. Find the angle between A, which is 4, 2, and B, which is 4, 2, then 3 minus 1. Okay. So what we can do? We can say that A times B is equal to modulus A multiplied by modulus B multiplied by cosine of the angle between them. So you can work out the cosine of the angle. Cosine of the angle between them is the dot product divided by A times B. So you can find A, modulus of A, which is square root of 16 plus 4, which is square root of 20. Modulus B, which is square root of 9 plus 1, which is square root of 10. And A times B is 4, 2 times 3 minus 1, which is 12, minus 2, which is 10. Okay, so A times B is 10. Modulus A, which is square root of 20, square root of 10. So 10, 10 divided by 10 square root of 2, which is 1 over square root of 2, which is square root of 2 over 2. And theta is going to be equal to the inverse cos of square root of 2 over 2, which is in fact 45 degrees. And let's check that. The angle. So I'm going to use the squares. 4, 2. So 1, 2, 3, 4, 2. So this is vector A. Vector A. And vector B is 3 minus 1. 3 minus 1. And this does look like a 45-degree angle. I mean, I can't say it by eye, but certainly it does make sense. 45 degrees. So I'm just going to assume that it is, that I haven't messed up anywhere. So scalar product allows you to find the angle between any two vectors just using the scalar product formula. So you kind of need both. You use both of them, right? You can't not use one of the formulas because it's not really you don't well, you're very rarely asked find just the just this scalar product itself. Doesn't always have a meaning. An example where it is used, scalar product, is finding work, for example. Work is force multiplied by the displacement. So in physics, work is force times distance, and it is force is a vector, displacement is a vector, but work is a scalar. Scalar, and these two are vectors. Okay, right. I think I'll stop here. I hope this was useful and interesting, and I'll see you next week for some more vectors and more 2D motion, the topic we have started. All right, I'll see you everyone next week, and enjoy. I'm glad to hear. Thank you. Bye.